Hello again, physics friends. Today we're going to focus a little bit on general relativity. So far, as you know, this class has been mainly about special relativity, and the main feature of special relativity is that objects are moving in straight lines at constant speed, so no accelerations. And we found lots of interesting features and outcomes in that case. But of course, in your day-to-day life, there's accelerations all over the place, right? We very rarely move in a straight line at constant speed. And so we'd like to understand a little bit about what acceleration does and how to account for it. And then, of course, gravity plays a big role in our daily lives, being as we are attached to the Earth via gravity. And so we'd like to understand something about gravity as well. In addition, we have talked about the twin paradox. The twin paradox we had resolved by saying that Alice in the rocket traveling to Sirius changes her reference frame, and in changing her reference frame, that is the resolution to the paradox. She's no longer in a single inertial frame, so her analysis and Bob's analysis are different in that way, and that breaks the symmetry in the problem. And indeed, Alice is the younger twin after she returns to Earth, and Bob is the older twin. Okay. But there was that perhaps unsatisfactory aspect of the twin paradox description where we have this turnaround where Alice slows down, stops, turns around, and speeds back up at Sirius. And we want to understand a little bit more about how this slow down, turn around, and speed up at Sirius can have such a big impact in Bob's clock. Remember, during that short turnaround period for Alice, Bob's clock jumped a huge number of years, and that because of RCA. But we want to have a more kind of physical understanding of why his clock jumped so much. In order to do that, we need to understand acceleration and how stopping and starting affect clocks. Okay. A key idea that we focused on in special relativity is this idea of an inertial frame, meaning a frame that is moving in a straight line at constant speed. And we said that if you are in an inertial frame, then your analysis is just as valid as any other person who also is in an inertial frame as well. And in the very beginning of the class, we talked a little bit about how you can tell if you're in an inertial frame. And you remember we said an inertial frame is one in which there's no acceleration. So objects that are not pushed or pulled on by a force would move in a straight line at constant speed in that frame. And we also said that your body has a lot of built-in biological acceleration sensors, like that feeling in your stomach when you rise over a hill in a car, or that kind of feeling in your ears when you know that you're spinning. Here's another way of thinking about acceleration. Imagine you are in a car and you're pouring water from a jug into a cup. If that water falls straight out of the jug and into the cup in your frame, then you are in an inertial frame, either at rest on the Earth or moving at a constant velocity on the Earth. But if the driver of the car suddenly accelerates and speeds the car up very, very quickly, and you pour out that water, then it probably would end up in your lap. So you can use actually the trajectory of water or a falling object or the angle of a pendulum that's dangling in your hand. You can use all of those as measures for acceleration. In an inertial frame, right, that pendulum would hang straight down, the water would pour straight from the jug into the cup. In an accelerated frame, the pendulum would hang at a tipped angle relative to the vertical. The water would not end up straight in the cup. Might end up in your shirt or in your lap. Okay, so that's what we mean by inertial versus non-inertial frames. And if we have acceleration, we are in a non-inertial frame. So we can think of acceleration as being a synonym for a non-inertial frame. So when Alice is slowing down, stopping, and speeding back up at Sirius, during that period of acceleration, she is in a non-inertial frame. So when Einstein was developing general relativity, the extension of special relativity to describe gravity and other accelerations, his kind of big aha moment was the so-called principle of equivalence. And it's really the fundamental idea that underpins general relativity. And you can frame it in the following way. We can say that a reference frame that's stationary in a gravitational field and one that's far from any matter, so not experiencing gravity, but accelerating at an appropriate rate will give rise to identical results for all internal experiments. That's a long way of saying that there's an equivalence between a gravitational acceleration and just like a propulsion-based acceleration. So gravity and acceleration have this very deep connection. So we're going to use this idea to understand how clocks are affected by gravity, and in turn, how clocks are affected by an acceleration, because this principle says that those are the same, they'll give the same result. This principle of equivalence is kind of the gravitational version or the acceleration version of there's no difference between being at rest or being in a frame that's moving at a constant velocity. So all inertial frames are equivalents. Here we're saying that there's another equivalence, and it's an equivalence between acceleration not caused by gravity, but just acceleration, and the pull of gravity. Okay, so gravity and acceleration are equivalent. So let's think through an example that will kind of bring this principle to life. Imagine that you are in deep space, far from any mass or matter, and you're holding a set of keys in your hand. And you're traveling at some speed in a straight line, measured relative to a very, very distant star. Okay. If you then hold your keys out and let them go, well, what are they going to do? Well, they're not going to fall to the ground because there's no gravitational pull on them. You're so far from any matter that there's no gravitational pull. They're not going to stay where they were a second ago because both you and the keys were moving along with the rocket at 100 miles per hour or whatever it is. So when you let them go, when you let those keys go, they're still going to be moving along with the rocket. Okay. So actually, in your frame, those keys will be at rest, and indeed, the idea, the principle of relativity, tells us that must be true, right? Because if instead of moving at 100 miles per hour relative to that star, you are at rest relative to that star, and you just let go of your keys in space, they're just going to hover there and float there. So you have to get the same result if you were moving relative to the distant star as if you were at rest relative to the distant star. So those keys are just going to sit there, and they are at rest relative to you and relative to the rocket, but they're moving at 100 miles an hour relative to the star. Okay, now imagine turning on your rocket thrusters. So that speeds up your rocket. And let's say you go from 100 miles an hour to 110 to 120. So you're speeding up. But the keys are not attached to you, and they're not attached to the rocket anymore. The keys are just floating in the cabin of your rocket. So they are not getting sped up by the thrusters of your rocket. So they continue to travel at 100 miles an hour. Okay. So each second, let's say you accelerate by 10 miles per hour every second. So for each second, the keys will appear to kind of move away from you towards the back of the rocket as your rocket speeds up. So although the keys are still moving forward relative to that distant star, and they're still moving at 100 miles an hour, in your frame, they will appear to be moving backwards at 10 miles an hour after the first second, and then 20 miles an hour after the second, and so on. Okay? So that's what you would see the keys doing if there was an acceleration of your rocket. Now let's imagine that we are floating out in deep space and we let go of our keys again, and the keys just float relative to us, and they appear to just be hovering in the cabin. And now instead of speeding up, let's imagine that we bring a very large planet near the rocket and put it behind the rocket where the thrusters were. That very large planet is going to pull on the keys and cause an acceleration of those keys towards the rear of the rocket. And if we're sitting there watching the keys accelerate, we would see the same behavior whether the motion of the keys relative to the rocket was caused by our thrusters being turned on and the rocket speed changing, or being caused by the planet's gravitational pull on the keys. In both cases, the keys would accelerate at a constant acceleration towards the back of the rocket. Okay, so that may be hard to visualize because I've just been speaking and not drawing, but let me draw now a picture to identify what I mean by that. And our basic idea here is that we're going to have two scenarios. Either the floor rises to meet the keys, or the keys fall towards the floor. In the floor rises to meet the keys, that's kind of thinking of it as a rocket is accelerating, and the keys fall towards the floor, that's kind of thinking of the situation in terms of the gravitational pull of the planet on the keys. So this is where it gets interesting. I'll draw this diagram out and we'll see how this plays out. Okay, so here's our scenario. We're in the frame of the key, and in this frame the key is at rest. So we're starting out in deep space, far from any other matter, with a rocket that's at rest relative to some very, very distant star, for example. And at this instant, we turn on the rocket thrusters so that it starts to move at subsequent times. Okay, but in this snapshot, in this particular diagram, the rocket is at rest in this frame, the key is at rest in this frame, the person is at rest in this frame, everything's at rest in this frame, okay? Well, if the key is at rest and the key is not attached to this accelerating rocket and it's not being held by us, it's just floating in the cabin, then for all of our subsequent pictures, which we'll draw on the right, the key has got to be in the same location because it's at rest and it has no acceleration. It's just staying there. The rocket, however, is going to start to move upwards. So on the right-hand side, we're going to draw the rocket at two other instants of time, okay? And at those two instants of time, the rocket will be moving higher and higher, okay? So here's the next picture. We see that the key is at the same location, but the floor of the rocket has moved up, so has the nose, so has the person, and now the rocket is no longer at rest, but it's moving. After this, I'll draw the next diagram. And here we see the floor of the rocket has once again moved up. The key is in the same place, but now the key has hit the floor. Or rather, the floor has risen to hit the key. We also notice that the velocity vectors are getting longer so that v2 is bigger than v1, because as long as the engines are on, we have an acceleration. Okay? And if we have an acceleration, then we have an increase in our velocity. So we have an acceleration in this case that points in the upward direction. We'll call that A for acceleration. Okay. So in the key frame, we could say that the rocket is accelerating upward, and as a result, the floor of the rocket rises to hit the key. So now let's consider a related but different scenario in which we're on the Earth and this rocket is just sitting on the launch pad, okay? The thrusters are not on, so this rocket is at rest in the ground frame, okay, and it's just sitting there. And in all of the pictures that we're going to draw for this frame, the rocket will continue to sit there. You're standing in the rocket, and you're holding up this key, and you let the key go. And under the influence of gravity, this key is going to fall down and eventually hit the ground. Okay. The rate that that key falls is going to be the same in this ground frame as it is in this previous drawing where the rocket is accelerating. The reason for that is that in this case, the key's at rest and the floor is accelerating up at a constant rate. In the ground frame diagram where we're on the launch pad, the rocket's at rest and the key is accelerating down because of gravity at a constant rate. So the principle of equivalence, which I've left over here on the left-hand side, is saying that if you were to measure the motion of this key from inside the rocket with no cues to the outside world, you would not be able to distinguish the first situation from the second. In particular, you would see that the distance between the key and the ground decreases over time with exactly the same profile in both cases. Right? So the time it takes from the release of the key to when it hits the ground will be the same whether you're doing a thruster-based acceleration or a gravity-based acceleration. And that's exactly the principle of equivalence. But there's a lot more to the principle of equivalence. And we don't have to go much further than this first diagram to see it, right? One of the things that we know is that all objects fall in a gravitational field at the same rate with the same acceleration in the absence of air resistance. So sometime you may have heard this principle of equivalence stated another way, that objects fall at the same rate due to gravity independent of their mass or shape or composition as long as you ignore air resistance. in shorthand, you can say something like a rock and a feather fall at the same rate, with the understanding that a rock is much more heavy than a feather, and yet if there were no air resistance, a rock and a feather would fall exactly in unison. And there's a wonderful accompanying video, again with Brian Cox, showing a rock and a feather falling in a huge vacuum chamber, and the two objects fall in exact lockstep. It's really gorgeous. So that's, if we go back to this bottom diagram, that's equivalent to saying, let's get a bowling ball. For example, I'll draw in a bowling ball here. We'll make it, how about green? How about purple? Why not? We have purple key and we have purple bowling ball. Okay, so we have our key and our bowling ball. These are two objects that are very different in size and very different in mass. And if you're standing there holding them both up at the same height, the statement on the left in blue is saying that the two objects, the bowling ball and the key, will fall at the same rate, and so they will land at exactly the same time. Now that might be surprising to many of you, and because in the ground frame it looks like, well, okay, gravity's pulling on the key, gravity's pulling on the bowling ball. Shouldn't gravity be pulling harder on the bowling ball because it's more massive and therefore accelerate more quickly? But let's look at this situation in the key frame, okay, where by equivalence, these two frames should be identical. And so any outcome that we reason in one frame should apply to both. Well, let's draw in this bowling ball. Okay, I have a bowling ball. It's just sitting there in space, floating in my cabin. And now my floor is rushing up to meet it. Well, who cares what the objects are made out of? The floor doesn't care, right? The floor is just moving. And of course, it's going to rise up and reach them both at the same time because they're just two objects at rest and the floor is approaching them. So this kind of bizarreness of a rock and a feather falling at the same rate is not at all bizarre if we use the principle of equivalence to understand why objects fall at the same rate. And that's just because a gravitational field, a uniform gravitational field like that found near the surface of the Earth, is fully equivalent to a constant acceleration, as we see in the upward diagram where the rocket has its thrusters on. So I think this is a really beautiful way of thinking about gravity, and this was Einstein's wonderful aha moment, this principle of equivalence. Incidentally, you might wonder why the bowling ball, like how do you explain that the bowling ball falls at the same rate as the key in the ground frame? And that has a very straightforward explanation. The bowling ball is much more massive, and then therefore it's true that the ground pulls more hard on the bowling ball than it does on the key, right? Because the force of gravity depends on the mass of the object that's being pulled on, in this case, the bowling ball. But it's also the case that a bowling ball, because it's more massive, is harder to get moving. So if you have a bowling ball and a key at rest, it takes much less force to get the key moving than it does to get the bowling ball moving. So there's two effects, and they're in competition with each other. And in fact, they exactly cancel out. So the bowling ball gets pulled on harder, but it's harder to move. The key gets pulled on less by the Earth, but it's easier to move in such a way that the two actually end up accelerating at the same rate. Now, if you are comfortable with mechanics, maybe you've seen it before in a physics course, you know that the force of gravity near the surface of the Earth can be written as the mass of the object times little g, where g is the acceleration due to gravity near the surface of the Earth. Okay, and we know by Newton's second law that the acceleration of an object is equal to the force applied on that object divided by the mass of that object. Okay, but if the force applied is mg, then these m's cancel, and we're just left with the fact that the acceleration of any object near the surface of the Earth is just given by a universal constant, little g. Well, it's not quite a universal constant, it's only relevant near the surface of the Earth. If you'd like, you can write this in a more clean way and a more accurate way by saying the force of gravity is due to the masses of two objects, like the Earth's mass and the bowling ball's mass, multiplied by a truly universal constant, big G, which is called Newton's constant, divided by the separation between those two objects squared, okay? And even if you write it that way, you can see that the mass in the acceleration term, force over mass, and the mass in this term, m1, say, the mass of the bowling ball, those are going to cancel. So the acceleration is going to be equal to g times the mass of the Earth divided by essentially the size of the Earth squared. And that's the same for all objects because the mass of the bowling ball has canceled out. So the only terms that are left are terms that are relating to the Earth. But if you've never seen this before, don't worry. We're not going to make use of it at all. I think this is a much more beautiful way, using the principle of equivalence, to understand why objects fall at the same rate, independent of their mass or their composition or their shape or their size or anything like that. Okay? So this is really cool. This seems to imply that gravity affects all objects independent of their mass or composition, like I said. Well, what about photons? Okay, what if we put a photon instead of a bowling ball here? What would happen? So let's explore that on the next slide. Okay, guys, this is where things get really, really interesting, right? Because the claim was the reason that the bowling ball and the key fall at the same rate has nothing to do with gravity necessarily. It just has to do with the fact that the floor is rising to meet them, or at least that's one way to think of this because of the equivalence between acceleration and gravity. Well, here we go. We're going to replace the bowling ball with a photon. And of course, the photon can't just be sitting at rest, right, in the rocket, because the photon speed always has to be the speed of light, 1 foot per nanosecond, in any frame. Okay, so we're going to make the photon travel horizontally, right? Because if we had the photon travel vertically, then of course it would arrive at the floor at a different time than the key because it has an initial velocity. But if it's traveling horizontally, right, then it would just be moving on this green dotted line forever, and eventually the floor would rise to meet it. So let's see what that looks like in a diagram, and I'm going to kind of draw a slightly different version of the rocket, just so I have a little more space for that photon to travel left-right, so our rocket's going to be more rectangular. Okay, so here we have a diagram. Again, we're in the keyframe, so the key's going to be at rest in all of our pictures, and we're shooting a photon from, say, the right wall of the rocket ship over to the left wall. Now, if there was no rocket ship, right, we would just know that the key has to be in the same place, right, as it was in the first diagram because it's not moving, and the photon is just going to be a little bit closer to the key, right, because the photon is approaching the key at the speed of light. So sometime later we'll have that, and then in the third diagram, now maybe the photon has just reached the key. Okay, so you don't even need to draw the rocket. This has nothing to do with gravity. This has nothing to do with acceleration. It's just a photon approaching a key. Then around the key and the photon, we can draw a rocket. Initially, that rocket is at rest, and but the thrusters are on, so there's an acceleration in the upward direction, just as before. This is the same problem as before. We just have replaced the bowling ball with a photon. But if that's the case now, the rocket will have moved upwards. Okay, so now the rocket's here. It still has its thrusters on, and therefore its velocity has grown from 0 to some larger number. We'll get rid of this little extra piece down there. And then, of course, the rocket continues to rise, eventually hitting the key. So we see that if you're in the rocket, you would say the photon is doing two things. You would say the photon has moved from the right side to the left side, but you would also say that the photon has fallen just like the key has, right? And I've timed it so that the photon arrives at the key at the same time the key arrives at the ground. So this is the situation in the key frame, but let's actually sketch out the diagram in the rocket frame, right? So here I'm drawing the picture at the time of launch of the photon. The rocket is sitting at rest on the ground. There's a gravitational pull by the Earth on everything, including the rocket, key, and the photon. And what we know is that as wherever the key is, the photon's going to be at that same height off the ground. Okay, so over time, the key is going to fall and the photon is going to travel but also fall. So we can actually just kind of sketch out the trajectory that the photon will take. It will not travel in a straight horizontal right left line, but it's actually going to travel in a parabolic path. Not a parabolic bath, a parabolic path. So that's kind of crazy. That's saying, if I shot a photon to the left, it's going to have a parabolic path. And if I threw a bowling ball to the left, it would also have a parabolic path as viewed from the frame of the rocket. Right, so that's the key point here. This is the rocket frame. And in this situation, this is a frame in which we're at rest on the ground. But we do have an influence of gravity pulling on the key, but also pulling on the photon. So the takeaway here is that light gets pulled on by gravity just like keys do. So the trajectory of a photon is affected similarly to the trajectory of a falling massive object. So what we see here is that gravity can bend light. In fact, as we'll see in the next slide, one of the very first tests of general relativity was this gravitational bending of light, in this case, the light from a distant star by our sun. So in the next slides, I'll show some examples of astrophysical observations showing how mass and gravity can bend light. So we now know that a gravitational field can impact the trajectory of the light. And what I'm showing here is an example of that. We have three objects, the Earth, so we're standing on the Earth, say, making an observation, and we're looking at a distant star, but in between us and the star is the sun. Now, the sun is a very massive object and exerts a very strong pull on objects around it. And as we saw before, that pull also applies to light. Okay, so this dotted line, or the dashed line rather, shows the trajectory that a photon from the star would take if there was no gravity from the sun, or if the sun wasn't there. So that photon would travel in a straight line on this page. But with the sun there, now we have this attraction of the photon towards the sun, or a bending of that photon trajectory towards the sun. So instead of going on the dashed line, that photon trajectory is bent inwards. So that does a couple things. Number one, the photon that normally would not have made it to the Earth is now going to make it to the Earth. Okay. And number two, it makes it look as if the star is actually in a different location, because when that photon arrives, it's arriving in this direction. And if you extend that line out, it'll make it look as if the star is over there rather than over here. So the position of the star relative to the sun is affected by the bending of the light. And we'll show that more in the next slide. So here we have exactly the same idea as last time. We have the light from the star. It actually comes on this solid trajectory. And because it came in this direction, if you extrapolate that direction back, it looks as if, from the Earth, it looks as if the star is actually here. Okay, this is the same idea of how lenses work. You have similar effects if you look into a pool and it looks like an object on the pool is kind of in a different place than it actually is, because the rays of light are getting bent by the transition from the water to air. Here, the rays of light are getting bent, but they're getting bent due to the gravitational influence of the sun. So if you were to look in the sky, you would see the sun in one place, and you'd expect to see a star very close to the sun, except this gravitational bending makes it look as if the star is further from the sun than it would have been in the absence of the gravitational influence. The problem with doing this is that stars, how many stars do you see in the daytime? Well, not many, right? And if you need the sun to be between you and the star, well, that's daytime, right? So how then are we going to be able to make this measurement in practice? And it turns out you can do it if you block the light from the sun. So how does that happen? Well, let's find out. Fortunately, we have a natural mechanism by which this light from the sun gets blocked once in a while, and that is a solar eclipse. So in 1919, Sir Arthur Eddington, a British astronomer and physicist, led an eclipse observation team to make measurements of the locations of stars relative to the center of the sun during the solar eclipse. And just as a refresher, a solar eclipse, right, if we're on Earth and the sun is here, a solar eclipse is when the moon is aligned with the Earth and the sun, such that the moon is blocking the light from the sun, but it would not be blocking the light from a distant star. Okay. Now this is really hard to see, and the quality of this image is not great, but these little green lines indicate the deflected star. So you can see a little bit on this diagram some actual star locations, and by mapping out where the stars are expected to be compared to where the stars are actually observed to be when the sun is there, you get a map of the deflection of each star. And when you do this, and when Eddington and others did this in this 1919 eclipse, they saw evidence for this gravitational bending of light in exactly the way that Einstein had predicted with general relativity. Incidentally, in Newtonian gravity, you can also make a prediction for gravitational bending of light just by treating a photon as you would treat any other particle, like a marble or a baseball. And Newtonian gravity also predicts that you would have a deflection of light because of gravity. And the Newtonian prediction and the general relativity prediction are similar, except they differ by a factor of 2. So for this observation, they were trying to measure the amount of deflection and see if that amount of deflection was consistent with Newtonian gravity or general relativity, and they found that it was consistent with general relativity. Now, since that 1919 eclipse, our observation tools have become much more sophisticated, and we're able to look much deeper into the universe to see more distant objects, more faint objects, and so on. And we have high-resolution satellite telescopes or ground-based telescopes that can measure the shapes of distant galaxies very well. One thing that you may have heard about before is gravitational lensing of galaxies, in which case, imagine the same scenario we're talking about before. So we still have the Earth and Sun and star in this case. But if you made the star more massive, you would get more bending of the light from the distant star. And so instead of just having the small deflection, you would have an enormous deflection, right? And if you were to, remember, look at this incoming direction and extrapolate it back, look how much this star would appear to have shifted on the sky, right? It's an enormous shift. Not just that, though. This is a problem that's fully symmetric, right? So if the Earth, the Sun, and the star are in a direct straight line, and light from the star makes it to you if it goes up and over, then light would also make it to you if it went down and up, right? Just by the symmetry of the problem. So in the next slide, we'll show that. And here we see that same effect. There's two ways in this picture for light to get from the star to you, and they're equivalent, right? But also, there's another degree of symmetry in this problem, right? If I take a line that connects the Earth, Sun, and star here, and I rotate about that line, then I'm symmetric, right? There, I have that degree of symmetry too. So actually, all of these directions, there's not just two directions, but there's actually a whole ring of directions, if you'd like, as I rotate this shape around. There's a whole ring of directions for which light from the star will make it to us. And so if you have this alignment, and again, not with our sun, but in an equivalent system using an object that's much more massive than the sun, you can get what's called an Einstein ring. An Einstein ring is the following. Now we are looking at the sun from the perspective of the Earth. So from our perspective, right, the Earth is on a line that goes through the center of the sun, and the source that we're looking at is also on that same line. So imagine like a line coming out of the page from this point in the middle of the sun. Towards you is the Earth, because you're standing on the Earth making this observation, and into the page behind the sun is the source, the distant star. And in that case, remember, we had shown that there were two lines that would come to you, but then we said it was symmetric. So all of these points on this outer circle represent photon trajectories from the distant source that make it to you. And so instead of seeing one object as a distant star, you would see a ring of light, even though the actual source was a point. So a single point source gets spread out into a ring of light, and this is called an Einstein ring. Okay, now let's see if we have any examples of this in nature. Okay, so here we have a picture showing some gravitational lensing. Let's zoom in a bit. What we're looking at here is a cluster of galaxies. So each one of these objects that I'm pointing to is a galaxy in a system that's gravitationally bound together. So imagine just a cluster, a group of these galaxies that are held together by gravity. But notice these arcs out here. These are objects that are much further back from this cluster of galaxies, and these arcs represent that gravitational lensing of those distant objects. And you can see that, look at the location of these arcs, they're kind of all centered on a point that's like around here. So the gravitational influence of these galaxies in the cluster of galaxies and other mass that's in this cluster of galaxies creates a lens that deflects the light from the more distant objects and creates these arcs of light. So in this example, before we had talked about the Earth and the sun and then a star. In this example, we have the Earth and then we have a galaxy cluster. And then in the distance, we have a bunch of individual galaxies. And the light from those individual galaxies is getting bent or lensed by this cluster of galaxies. Okay. Now here are a bunch of examples, 8 examples of Einstein rings or almost Einstein rings. So we have a yellow object and a blue object. The yellow object is a galaxy that's between us and a distant source, and the blue object is the distant source, very, very distant source. And although the blue object looks like it's a ring, it's actually essentially a point source, okay, that gets lensed into a ring. So these are real-life examples of gravitational lensing by a central galaxy of a very distant object. Okay? And these were discovered by the Hubble Space Telescope. These measurements were made by the Hubble Space Telescope. And since this time, this was about 15 years ago, there have been many more examples of such gravitational lenses and Einstein rings detected. So this is a beautiful real-life example of general relativity at work. And continuing with our pretty pictures, here I'm showing a lens system that was discovered in, I think it was 2007 by the Sloan Digital Sky Survey. And they found this ring. This image is not from the Sloan Digital Sky Survey. This is actually an image from the Hubble Space Telescope. And you can see here this beautiful example of lensing by a central object. And also just look at the absolute gorgeous picture. I mean, each one of these little dots is a galaxy, a whole galaxy with billions and billions of stars. It's absolutely amazing what's out there. And this just represents just a phenomenally tiny patch of the sky. So it gives you pause to wonder what else is out there that we don't know about. This gravitational lens being just one example of something that's phenomenal and gorgeous. But the universe is a mysterious and beautiful place. And we don't ever want to forget that. And as if the universe just has this glorious sense of humor, here is what's known as the cosmic happy face, where we have 2 nearby objects and a lensed background object or objects forming a cosmic happy face, 2 eyes, a nose, and a mouth. You never know what you're going to find when you start exploring, either here on Earth or out in deep space. I think that's a nice note to close on. In our next video, we'll explore something about how gravity affects time, now that we have a sense for how gravity affects light. And once we understand how gravity affects time, we'll be able to get a deeper understanding of the physics behind the twin paradox resolution. Until next time, my friends, be safe and be well.